Purpose of this video is to talk about using an extended Kalman filter to do what I'll call parameter estimation, or also I could call it real-time system identification. So let's look into this. In the good old mass spring damper system, where we assume a linear spring constant and a linear damping constant, we could do our state space magic and come up with this two state variable state space model, and everything's fine. We could use a Kalman filter to do this job, not an extended Kalman filter. Everything's nice and linear. So we can use the Kalman filter to do this job. But what if we don't really know those spring and damper constants? Or what if they're not really totally linear? What if they change a little bit by position or by time? Well, one way to deal with that is to make them state variables and use an extended Kalman filter. So we had the X1 and X2 state variables. They were just position and velocity of the mass. I'll say, look what we had here. Here's what we had in this little this continuous time state space format. Minus K over M and a minus B over M for the constants and the mass. Now I'll make those guys state variables themselves and make it a 4-variable state vector. Call X3 this K over M and X4 this B over M. I'll say X3 dot is 0, but I'll say X4 dot is some. Here's where I'm going to put my tuning parameter and inject noise into my system model. We talked about tuning parameters in the previous video. And how you do that is kind of a designer's choice. I guess I could have put some here or could have put some noise on both. Well, let's say we just put it on this one guy, this X4 variable, the damper constant. Then X2 dot, which was this in the linear situation, now these guys are more state variables. So here it is all in terms of the 4 state variables. So here is our state variable, a state space representation of our new system. And now it's nonlinear because of this second line. And we added some process noise, even though it wasn't really process noise on this system. We injected it so we could tune our extended Kalman filter. When we do this, that can be called parameter estimation. We're estimating the parameters of our system. Normally consider them parameters. Now they're state variables. Or I could call it real-time system identification. We're trying to figure out what the K and the B are. Do that in real time. How's that work? Well, let's first, how do we go about doing that? I'll go through this quickly. We follow the complete guide before, or the recipe that I talked about in the previous video. So here's our F now. Here's our G. This capital F, this is the little f. The capital F is this matrix of partials. Let's see. This guy would be the partial of this with respect to x1. Well, there's no x1 in it, so that's 0. With respect to x2, it's just 1. With respect to x3 and 4, it's 0 again. This guy would be this partial derivative with respect to x1, which would be minus x3. This guy would be, this guy is partial with respect to x2, which is just minus x4, etc. Very easy partial to take. And these guys are all zeros. Here was our way to compute p. It's basically this matrix multiplied by a tau, and then add ones along the diagonal. It's easy enough. And then the phi at each time step is this guy replacing every tau with capital T, which is your time step between measurement samples. Everywhere there's an X in here, you're actually going to calculate it at your current estimate. Okay, we got to do Q, which means ultimately taking this. First, we got to find out what this is. That. To do that, we'll first find out what this is. So we got to do a matrix multiply. We had the phi, we had the G. Here's what it is when you multiply. Now we multiply that result by its transpose. This is all back, we talked about that stuff in Kalman Filter. You do that matrix multiply, you get this. You integrate this thing over tau as tau goes from 0 to capital T. And everything here is just some multiple. It's either a constant, a tau, or a tau squared. So those are easy to integrate. Integrate from 0 to capital T. Again, all evaluated at the current estimate. So here's a summary of all the things. Put into a computer. This is what you calculate ahead of time. Then put it into a computer, and your computer crunches the numbers. They come in over time. How does that work? I forget what green and blue are, but one's the true position in this case. One is true and one is the filter's estimate. This is position. This is velocity. No, these are all position. All these top three are position errors. This is a position. These aren't position errors. These are true and estimates of position along the top. This is a position error for one case, along with the filter's estimate of its own accuracy. The one standard deviation confidence limit, and it looks pretty good. I mean, your true errors generally stays within those confidence bounds. And here's for those parameter states, x3, which I think was spring constant, and your x4, which was your damper constant, and it's their error covariances. We put zero process noise on this state, so the confidence interval is going to keep shrinking to nothing. It might not be a good thing. It looks pretty good here. And this looks pretty good as well on the damper constant. Kind of summarize it in numbers instead of graphs. The only thing we measured was the position with an accuracy of 0.1. Here's some true values for the basically the spring constant and the damper constants. And here's where the actual RMS errors, not the filter's estimate of them, but the actual error between the estimate and simulated truth. In position, we had these accuracies when we only, these are at steady state or after some settling time. We measured to 0.1, but look, we estimated to less than 0.03. These were the spring constants, but our errors in them were like 2 orders of magnitude smaller. The damper constants were like these, and we're like at least 1 or 2 orders of magnitude, mostly more. But anyway, I consider that not bad. We did a fairly decent job of estimating not only position and velocity, but those unknown parameters. Anyway, that's all I want to say about parameter estimation or real-time system identification.